So let's begin with the 11th number lab. Can you see the screen?
Yes.
Okay. So today we will be wrapping up this simplified LTE system. So we will be covering the last three blocks, which is the FEC Decoder, Deinterleaver, and BER computation. So mostly the things I have already explained during the transmitter side. So actually the transmitter side, I have explained also some aspects of the receiver side. So if you have any confusion with the working principle or something, you can go back through that concept, those lectures, and there you can find the details. So I'll be skipping the details so that not to be redundant again and again. And if you have any confusion, you can then ask me through email and I can still explain you. So today we will be finishing this 11 number lab, and I'm also planning to give you an assignment. So I'll probably upload it during this weekend, and you will have like maybe 1 week or more than a week for attempting your assignment. And after that, yeah, we will be doing some real-time experiment, like collecting some data from the real-time, from the Wi-Fi, for example, using the Wireshark in the next lab. So we will be collecting data, and then we'll try to process it in the MATLAB. So that will be a very interesting thing. I'll try to wrap it up in 1 or 2 labs. I'll see how much time I have because you also have your final exam. And one more announcement is like on the Tuesday, I think which one is that? Uh, I think it's the 1st of June. I'm not sure, but I'll confirm. That class is swept. So the professor class is swept with me. So I'll be taking the lab session in that, and then professor will be taking the course and my lab session, which is on Thursday. So that is all for today's announcement, and let's get started with the lab. So so far we have covered up to the demodulation. So we saw all these blocks: bits generation, reshaping matrix, then having coding, block interleaver, and then some modulation scheme, and finally some of the erratic channels. And then we use the equalizer, and then finally in previous lab we studied the demodulation part. So you can see that and the this is the transmitter side. Now from the random bits to the modulation. So all these blocks are related to the transmitter side. This one block is related to the channel side. So the channel is wireless medium now. And then all these blocks are related to the receiver side, which we are currently dealing with. So what is the transmitter side? Transmitter side is the base station. For example, the big towers that you see on the top of the buildings or on the hill or mountains. So there you those big base stations are your transmitters, or they are your base stations, and they are going through all this stuff. And then when they radiate the signal in air, it is going through some channel degrading phenomena. And we have model then we saw some two types of models, the channel models. One was the AWGA and also the relay channel model. And the relay channel model is specifically for non-line of sight communication. And if some transmitter and receiver can see each other, then that one kind of channel model is the rich channel model. Then we saw also the zero forcing equalizer, and also I briefed you about some other types of equalizer in the previous lab. And then we covered the demodulation part, and we covered the bit stream from the complex BPSK demodulation. From the modulator that it were basically giving you the coordinates information, the modulation part. So those are already complex. Those were complex, and from here those complex were changed back to the actual bits information. Now today's what we are going to cover. We are going to cover the FEC decoding, and then we also will cover the block Deinterleaver. And finally, we will see how much errors occurred when we were transmitting the bits here, and when it passed through all these models and from the channel, and then it reached here at the receiver side. So here we will see how much error occurred that we can see on the bit error rate. So the Hamming decoder, I think I had already explained you in the Hamming part of the lecture how we are going to make the source data. Then source data is encoded, and then parity bits are added. And then I have also explained to you how the parity bits are from the information of the parity bit, we can recover the actual bit, and we can correct up to the maximum 1 bit of error. So I hope you can easily find all those information from the previous lecture that I had already covered. So we were transmitting the source data. The source data was less number of bits, but then we added some redundant bits, some extra bits with those source bit, and we called it the parity bits. And the parity bits were added just for the sake of any immunity of error. So if there is any error occurs from transmission to the reception, then those errors are compensated or they are removed just because of these extra redundant bit. So what was the pros? The pros was the advantage was we are adding the extra bit of information, and then we can recover the bits with least amount of errors. What was the cons? We are adding extra information. So when you are adding extra information, that is kind of increasing the overhead, and that leads to increased number of bits transmission. When you are sending more information or more bits, that will also, I had explained you, there is some collision occur, or the bits are with the more bits there will be more errors. So when you're transmitting more bits, more data rate, that means that you are having more bit error rate. At the receiving, what we will be doing from information of having the parity bit information that we had added here, we will be trying to recover the bits with no error or least error. And then we will be also taking off those extra parity bits, and we will be only extracting those key information. So the information that we had transmitted on the transmitter side, we are trying to recover it on the receiver side. So Deinterleaver. Deinterleaver, I had explained you in very detail in my previous Interleaver class. The purpose of Deinterleaver was to remove the burst error. What was the burst error? If you are sending the bits back to each other, so if the error occurs, the deep fading occurs, all the back-to-back errors are corrupted. We don't want that, because we want the uncorrelated bits. If the uncorrelated bits are corrupted, that's okay. But if the correlated bits are the close bits, which are moving very close to each other, they are corrupted, then it will be a big trouble. So what we were doing there, we were basically transmitting this one column wise, and then at the receiver, at the Deinterleaver side, we will be receiving those columns. So we will be arranging it in the columns, and then we will be extracting the data row wise. So it was like this: we input the data in the form of rows, we extracted the data in the form of columns, but in the Interleaver section. And the Deinterleaver section, the Deinterleaver will take the data in the form of columns and then extract the information in the form of rows. So what we had transmitted here, for example, x0, x1, x3, they will be received exactly at the same sequence, x0, x1, x2, and we will also deal with that problem, the burst problem due to the deep fading. Okay. And then we have the bit error rate calculation. So I think you see this figure, you have seen this figure a couple of times. You have the transmitter, and then you have the receiver, and then you have the channel. So every time I keep telling you that the channel is composed of a lot of errors. So it depends on it's like stochastic. We never know what kind of errors are there. There can be people moving, there can be trees in the path of the signal, there can be different scatters. So all those scatters reflect, absorb, or different thing can happen to the signal. And when the signal is transmitted here, because of those reflector, diffractor, and absorption that I already explained you before, the the bits become erratic like this. So for example, you had transmitted a sequence like that, but at the receiver, you receive something like this. So you can see that this was transmitted as 1, but here the rate it is received at 0. So the 1 bit is flipped somehow to 0 because of the error in the channel. As this is also corrupted. This is just an example. It's not like exactly this bit should be corrupted, but it depends on the nature of the channel. So if the channel is more corrupted, some particular bits gets corrupted, and when those bits corrupted, despite of we removing the we are putting the filters there, we are putting the equalizer there, or we are doing everything that FEC decoder there. So we have done all the possible best ways we could have done. Like we use the channel encoding, we use the equalizer, we use the filters. Despite of all those efforts, if there is still some error at the receiver, then we should calculate using the bit error rate. So what is the bit error rate? There are several ways to calculate the bit error rate. One of the ways, for example, is to just see the signal which was just transmitted and then compare it with the signal which was just received, and then see what is the difference between the transmitted and the received one, and that will give you the bit error rate. From there, we can see how much bit error rate is this, and then we will also see the plot of that one. And then we will compare. If you are sending less information, then there will be less bit error rate. If you are sending more information, there will be more bit error rate, right? So more information means high data rate. High data rate means that you are increasing the spectral efficiency, but on the other side, you will be having some more errors. So I think that is all enough for the explanation. And then let's move to the MATLAB part now. So can you see the MATLAB?
Yes.
Okay, thank you. So what we are going to cover in today's lab, we are covering the FEC decoder. Then we are covering the Deinterleaver. Then we are covering the bit error rate calculation, and that will conclude our whole session on the LTE. Okay, so the bit error rate is very important to see the for example, you are using different channel encoding. Channel encoding means you're using the Hamming coding, you're using the turbo coding, convolution coding, and then you are using, for example, the BPSK for all three of them. And you want to see which one is more efficient. Hamming coding is better, convolution or turbo coding is better for using the same sequence of bits. So you can see it from the bit error rate calculation. Or you can see, for example, I'm using the Hamming coding like the way we are doing now, and we are increasing the transfer of bits per symbol. So we are sending a BPSK 4 QAM, or you can transmit it to 16 QAM, 32 QAM, 64 QAM, etc. And then at the receiver, when you say that, okay, I had the Hamming coding, but I was only increasing the data rate at the transmitter side. So what would be the bit error rate when I was transmitting the BPSK? What was the bit error rate when I was transmitting the 4 QAM, and what was the bit error rate when I was transmitting the 16, etc. So all those things are the behavior of the channel you can see with the bit error rate. For example, I'm using the Hamming coding, I'm using the BPSK, but I'm using three types of channel or two channels. For example, I'm using the AWGN, and I'm using also the relay channel. And then I transmit the same information. The channel coding is fixed, the transmission bit is fixed, only I'm wearing the channel model. And then at the receiver side, I can see from the bit error rate, what is the bit error rate when I was transmitting, for example, through the AWGN, and what is the bit error rate when I was transmitting through the relay channel. So all these comparison you can see with the bit error rate calculation, and it's quite important. So first of all, I'll start with the linear decoder, or what we had done here. For example, if you see uh, this one. So previously we had used n is equal to 7, k is equal to 4. So we will retain those information because we shouldn't change it. When you had transmitted n with some different number and k with different number, then you should also use the same information at the decoder. Okay, so these are the information. It means that you are adding three parity bits here. And at the decoding, if you are saying that I use, for example, 7 parity bits, then it means that what you had given the information, you had added only 3 parity bits, but you are expecting 7 parity bits at the receiver. So it will also consider your data as the parity bits, and that will further corrupt your signal. That will further give you more error. So you have to retain the same information. These information should be known by transmitter and receiver, and they should be fixed. If n is 7, k is 4, at the encoder side, at the decoder side, they should be also n7 and k4. Right. So let's keep it as it is. And instead of encode, let me copy this one. For example, okay, only this one portion. Let me copy this portion, and I am pasting it here. And instead of encode, I should say just decode. Right. So I think that will do my work. And for example, this is my first one. So I should say this is the AWGN. So I have two modulation scheme. One is the BPSK, which I had expressed with 2, and one is the 4QAM, which I had expressed with 4. And then I had two channels. So one is the AWGN, and the other is the relay channel. So I hope you already remember all those informations. So for example, I am saying this one. AWGN. This is related to, sorry, this one. This is related to AWGN, and then this is related to the linear LIN, and then this is related to the BPSK. Right. So I think this gives me the whole information. I'm going to decode this information using the same parameters that I had used at the encoder side, and I want to decode it. Okay. So let me copy it and let me paste it here. So now I'm doing it for this part. So I will replace this part, and then I will use, instead of BPSK, let me use 4, only 4. For example, I'm using 4 QAM. And then I can copy these two, and then I can just paste it. And instead of this one, I should replace it with this one, and this one I should replace it with this one. And then it is not AWGN, so it is the Ray channel. So Ray CHAN, and also this one has the Ray CHAN. So if I run it, But I think I did a mistake. Yeah, I was expecting it because the we are this is still in the matrix form. So if we see this AWGN D2, this one, for example, so it is still in the matrix form. So we should feed the data and column by column. For example, we should queue the first column, and then we should queue the second column, then we should queue the third column, up to the, I think we have 1 or 2, 4 columns. So we have 1 or 2, 4 columns. Okay, look at here. So we had the actual bit that we had transmitted, they were 4. So we actually transmitted 4 bits, not exactly in sequence order, but we had transmitted 4 bits. But then 3 were added is the parity bits. So I'm just highlighting it. It doesn't mean that the first 4 were the data and the last 3 were the parity bits, just for sake of information. Maybe this was data, this was parity, then these 2 were data, then this was parity. But we had transmitted the actual bits, the K informations were 4, and the N we received is 7, right? Now this was the first one, then we transmitted the second, then we transmitted the third, fourth, up to the 1 or 2, 4. So now we are in the decoder side. We should give the first column there. We should feed the first column there, and we should expect the 4 answer, the 4-digit output, which should be exactly the same as what we had transmitted. So let's go there, and we should feed the data in the form of columns. Right. So what are the columns? The columns are this one, and not only one columns, but all columns. Okay. So how to do that? So let's do it like this. So if I use this command, for example, length of, and I just take, for example, this one, it should be, oh, sorry, not this one, because it is not recognized yet. This one. So this is 1024. But if I use the other one, which is, for example, this one, or let's say this one, it should also be equal to the 1024 because the dimension is not changed, like the way we saw in our slides. So the dimension is similar. 1024 is here, 1024 is here, 1024 is here. So that is not affected at all. So the length is always similar. So we can use any of the length. So for that sake, we can use for I is equal to 1 colon length of any of them. Just take, for example, this one. So the only goal is to get the length of that, and then you can simply say, okay. So if you want to make it well aligned, press Control I, and it will make it very well aligned like this with the for loop. You can see that it is something happening inside the for loop, and there is the space automatically coming there with the Control I command. So how do I do this? The all columns. So I can do the all columns by just copying this information like this. So it means all columns. So please remember, the first thing always in the matrix shows you the first dimension, which is the rows. The second will show you the columns. It's like in matrix. If you say that it is n class M matrix, right? So n always shows you the number of rows, and M always shows you the number of columns. So I'm saying colon means everything there, and this I means the index, which is incremented by the for loop. So every row in the first column, which means that every row in the first column. Okay. And I should copy this one, and I should paste it here. Paste it, paste it. Now let's run it. Something wrong. LENGTH. Okay, that's it. And now if I see this one, for example, AWGN linear, where is that? Linear BPSK. See, before I had 7, but it automatically removed the parity bits, and now these are the information which is exactly related to the K, the information that we had transmitted. Okay, so this is what we have also for this one, and for this one. Then you can check it later. Right, so I think we are done with the FEC decoder. It was quite simple. And now let's deal with the Deinterleaver. So I told you we transmitted it column wise. So we have to receive it column wise, right? So for that purpose, we have to take the transpose of this one, right? So transpose basically transform the matrix shape. If there are n rows and m column, it will transform it into m rows and n columns. Okay, so I hope you already have some basics of the linear algebra. And transpose is very easy in the matrix. You just paste it like this, and this is equal to, and then the backdash, just the upper comma. So this will take, I'm just not changing the name of the variable. So I'm taking this this variable, which contains the vector information related to the decoding, and then I'm just simply expressing it in the form of transpose. So I will do the I will put this one, and it will take that transpose and keep it here. So let's do it for all. This one, take this one, and take the transpose of this one, and save it at the same variable. And then I'll take this one, and I'll take the again the transpose of this one, like this, and the same variable, and finally the last one. All right, so this is for the first one, the second one, the third one, the fourth one. So we interchange the rows and columns. So if the matrix was like this, we made it like this. Okay, so we just flipped it. We didn't do anything wrong with it. We only flipped the number of rows and columns. We just make it different. We are now showing it in a different shape by doing the transpose. And now we can just feed it directly to the matrix D interleaver. So let's go back and see that command in the interleaver side. And it was here. Right, so it was something here. So I'll just copy this information from here, and I will paste it here. And instead of linear interleaver, linear code, let's say put something like that. But I don't want to interleave. I want to de-interleave, right? So for the de-interleaver matrix, let's Google it. Matrix de-interleaver MATLAB. Oh, not the Simulink block. I should use the Deinterleaver. There is also this one, but I think there is a simple one. Something like, if I Google this one. Yeah, so I think this is the matrix Deinterleaver, right? So it's exactly doing the reciprocal of what we had done for the matrix interleaver. So let's go back to our this one, and here I should use the Deinterleaver here. Matrix Deinterleave, right? So this is the input which is coming from here, and what is the number of rows and the number of columns. So we didn't change it because we should keep it the same as we had done it in the transmitter side. So let's say I'm saying at the AWGN, the first one is related to the AWGN, and then it is related to the linear coding, and then let's say it is related to the BPSK, and then it is equal to. So delete it. Okay, so this one contains the information which will convert this back into the matrix Deinterleaver form, and it will recover the original bits that we had transmitted. So let me copy it several times. Okay, and then let me copy the for the region and also for the region 4. So we input all those information here, and then AWGN BPSK. So let me call this as 4. Because it is 4, right? So I'll call it 4. And then this one is ray channel. So I can say that this is the ray channel. So instead of AWGN, I should the ray channel. And also instead of the AWGN, I should use the ray channel. And then this is 4. So I should also use the 4. Okay, I think fine. So let's run it. Okay, very good. So if I see this one, for example, the AWGN linear BPSK, no, not with underscore, AWGN linear BPSK, for example. So it exactly contains the information in the row form which we had transmitted there at the transmitter side. So we extracted the information like this now. Now let's go back and calculate the bit error rate. This is the most important one. So the bit error rate requires, there are several ways to do this, but let me use one of the very simple way. I want to see the bits that we are transmitting right after the modulation and the bits that we are receiving right after demodulation. So we have something after modulation, we have something after before demodulation. So what we are calculating, we are calculating the impact of the channel. So if we are transmitting something in the erratic channel, before that we modulate it. And when we receive it, so we will, right before the demodulating it, we want to see what degradation happened into the bit information, right? So let's do it. I will say put some parameters here. For example, the signal to noise ratio are ABN0. Let's say I'm using it for 1:1:12 dB. So it will compute a matrix on the x-axis, and it will calculated. I will show you this thing in detail when I plot it in the diagram. So just mm, let me do the other stuff, then we will come back to it. So what are the symbol in the BPSK? There were two symbol in the BPSK, and what were the symbol in the uh, 4QAM? There were four. And let's say I'm not using, so I need some transfer function like thing. So I say that I have nothing, the denominator is just one. So, and also I'm using the numerator for the BPSK. So I'm using a simple numerator, just the ones vector. So there are two symbols, and then divided by two. And let's say for the four symbol, I should use the four. I'll call it 4. So the information related to BPSK is 1, 1, and the information related to the 4QAM is 2, 2. Okay, so just remember this thing. And then since I'm transmitting a lot of symbols, so I want to take some sample from that and then plot the Embed error rate. So and sample, and let's say I'm taking 100 sample from that one, and I hope that will be enough for me. So I have two things to transmit. One is TX underscore BPSK, and the other is TX underscore 4QAM. Since I used two modulation, right? So I was transmitting the BPSK and I was transmitting the 4QAM modulation. I was doing these two modulation. What I was receiving? I was receiving BPSK using AWGN with the AWGN channel. Then I was receiving the 4QAM with the AWGN, right? And then the uh, I was receiving the BPSK with the array channel, and then I was receiving the 4QAM with the array channel. Okay, so let's fill this. Let's go back to the modulation, and in the modulation, I was modulating BPSK, so I should copy this one, and the transmitter BPSK was this one. Let's go to the 4QAM. So the transmitter 4QAM modulation, it was this one, and I'll copy it and I will paste it like that. So I'm scrolling up, scrolling down, and then copying the relevant information from there. I'll give you the source code, and then you have to please go and look back to this and what it is and why I'm doing it, so that you can understand the whole story there. Okay, so you have to go back. What was the transmitter BPSK? What was the receiver, the receiving for the transmitting for QAM? And when we received it, why I have four? So why I have four? Because I have two channels, and each channels within each channel, whether it is AWGN or array channel, I have transmitted the BPSK and also the 4QAM. So in total, I have received four. So let's go to the receiver side, and here in the 0 forcing, I received this one. This is happening right after the channel. Okay, so I'm only observing the impact of the channel. So 0 forcing linear AWGN2. So this was what I received for the AWGN2, and then I will go back, and then I will copy this one, which is AWGN4, which is this one, and then for the array channel 2, I will paste it here, and also for the array channel 4, I will paste it here. So I think everything is ready, and now we have to use the built-in MATLAB function to plot the bed error rate. So there is something CB analytic in the MATLAB. So analytic. So this is the one. Let me copy, and this is computing the bed error rate. So let's go back. Sorry, let's go back. Paste it here. Semi-analytic, what is transmitted symbol? So I'm using it for the first one. So this is transmitted BPSK, and what was the received BPSK? That using the AWGN channel. So it was the AWGN channel. And what was the modulation for this one? So it was this one. So it was M1. And what is the number of sample? So N sample is this one. So I think we have everything now. And then this is for the bed error rate underscore LINEAR linear channel, and for the AWGN underscore 2. Okay, is equal to, okay, sorry. So I'm computing the bit error rate for the linear FEC encoding and using the AWG channel, and then the information is for the BPSK. So let me copy this big syntax and paste it a couple of times. We will just do the corresponding channel changes for. So let's say 2 error for the AWGN, and this is for the array channel. And also I'll copy the array channel information from here, and instead of AWGN else. So I have 4. So now this is this one, transmitter 4 QAM. So I'm using the 4, so I'm transmitting 4 QAM. What was the 4 QAM received at the AWGN? The 4 QAM at the AWGN was this one, and modulation type. So I'm using, let's say, this modulation type. This is the built-in. Let's say phase shift key, non-differential. So there are different. You should use this for all. Okay, and then for the 4 QAM, I was using M2, and the number of sample is different. So for 4 QAM, I was using the M2, and all the rest of the things were like that. For the array channel, since it is the array channel BPSK, I received the BPSK array channel here. So I will only change this one, and I will compare it with the transmitter BPSK. And the array channel QAM, I use this one. Okay, and then transmitter BP, instead of transmitter BPSK, I'm transmitting the 4 QAM. So let me go through it once again. Transmitter BPSK, and I'm receiving BPSK with AWGN channel, and then I'm using all the parameters that is related to the BPSK. Then I'm transmitting the 4 QAM, and then I'm receiving 4 QAM with AWGN channel and all the information which are related to the 4 QAM. And then I'm transmitting the BPSK with the received relay channel, and then I'm using the information related to the BPSK, and then I'm transmitting the 4 QAM and receiving 4 QAM with the relay channel, and I'm using the information related to the 4 QAM. Okay, so I think I already have these 4, and I have let's plot it now. So let's say I'm calling it figure number 1, and there is similogy plot. SIMILOGY. Yeah. So this is the plot. Here, the x-axis is EB and 0, which I have already defined there. This one. And then I will plot it with this one. Okay, so x and y axis, and then I will hold on because I want to see the impact of all of them with varying channels. And then let's say I'm just copying it and paste it for all the 4 of them, and then copy the second, paste it in the second, copy the third, paste it in the third, and the last one, and then just paste it in the last one. And then let's label it more to make it more clear. Grid on, for example, I want to see the grid also. X label is EB and 0. What is the Y label? Y label is the bit error rate, and then the legend. So let's say the name all of them. We have 4. So I have AWGN 4 QAM. I have the AWGN BPSK. I have the relay channel 4 QAM, and I have the relay channel BPSK. Okay, and let's run it. Okay, finally we saw something. I see. So we should decrease that one. I think we should play with this number. It's too much. It's not too much. So what it means that let me show partial of the like this portion. Okay. So this one, this is AWGN with a BPSK. So if it is a BPSK, that means we are sending less number of symbol. So it is having the least bit error rate, and the signal to noise ratio is this much. But if we are using the AWGN with the 4 QAM, which is the blue, so it's this one, and it's far away from here. So that is the main difference. Like if we further increase it, I think that is too much still. Yeah. So then the ray channel. So here we can see how much is the gain of this channel over this channel. So the ray channel can achieve something at 12 EPN 0, but that can be achieved by the AWGN channel at around 4. And then you can also compare the four of them. For example, AWGN blue, this is for the 4 QAM and this is for the BPSK, so the difference is a lot. And also the difference between the RAVE, which is the 4 QAM, and this is the BPSK, so that is also a lot. So I think I have used a very big value. We should use try to use it with a small value. I will work on the code just after your class, and then I will upload it to your course web. And yeah, this is all for today, for this one. And we already covered the LTE system, a very simplified model of LTE system. So do you have any question? If you have any question, yeah, I can answer you. I'll take your questions. And if not, yeah, then you can leave. Okay, so regarding the assignment, when do we get assignment? Yeah, I'll try to make it maybe, yeah, before the weekend, and yeah, I'll post it on your iClass, your course web. You can check it there, and yeah, it will not be difficult. It will be. I want to make something related to this LTE. I'll make little changes. So if you have anything you want to find something, I showed you the way. Like just copy the command or just Google it using the MathWork website. Type some keyword and space MATLAB, and it will gives you the exact command, and it will also give you the description how to use it. So I'll be not giving you very tough assignment. That will be very easy for you. And yeah, just try it and try to understand also the BER calculation. And yeah, once you understand this thing, then the whole story will be very clear to you. So yeah, that's all for today. If you don't have question, yeah, you can leave. Okay, so I'll see you in the next lab, and yeah, bye bye.
Thank you.
Yeah.